So let's get going, and then we'll do all things. So rock is thrown straight up. Off the top of a 64-foot building. With an initial velocity it always feels silly to write this stuff out for you guys, but like, you know, it's kind of standard. Velocity of 48 feet per second. Sure. So here's what we want to ask. I'm sorry, where's my first question? So the thing I really want to know is, how high does the rock go? And I probably haven't given you quite enough information yet. So let's talk about the kind of formula for the height. So the height at time t in the in the US system of measurement is given by this equation. Negative 16t squared plus 48, so really I should just give you the general formula. Plus initial velocity times time plus initial height. That is your very, very general position formula in the US system. If it was the metric system, instead of 16 here, you'd have 4.9. Because that number there is half the constant for gravity. And then I will also point out that the velocity at time t is equal to the derivative of the position function, which is equal to negative 16t. And I should say this is in feet. Negative 16 times 2t, apologies, plus the derivative of v naught t is just v naught, or more generally, the derivative of a constant times your variable is just the constant times 1. And the derivative of a constant is just 0. So this is equal to negative 32t plus v naught, and that's feet per second. And then finally, and really we're kind of doing this backwards actually, but that's okay. Finally, the derivative of velocity, which is acceleration or the rate of change of the rate of change, which is the second derivative of position, is the derivative of this, which is just negative 32. And that's feet per second per second. Wow, that doesn't look like an S. That's a, which is negative 32 feet per second squared. But I do really like to say it's negative 32 feet per second, because what this means, right, your rate of speed is changing, right? It's getting more, right? If you have an object that's falling, its speed is increasing. It is accelerating. So that's why you're changing at a rate of negative 32 feet per second. Okay, so these are the equations. You probably want to know them. Really, what people have actually done is they've taken this constant for gravity and they've anti-differentiated to get back to the velocity function and the height function or position function. But we don't really have that tool just yet, so we're going to think about it this way. And so then we can ask all kinds of questions like, how high does the rock go? How fast is it accelerating in a certain time? Really by just using these equations. So in our situation here, we have the height equation. So the height at any time t is going to be negative 16t squared plus our v naught, which in this case is 48 times t, plus our h naught, which is 64. And our velocity at any time t is going to be negative 32t, plus 48. And I don't really think we need to write down the equation for acceleration again. So what kinds of questions do we want to answer? Well, I asked how high the rock goes. But maybe we could ask a few other questions first. And I feel like I just wrote those, but I kind of want to write them again. Sorry. And it feels kind of silly, but just so I have them over here. Great. So maybe I want to ask questions like, how high is the rock when t equals 1/2 a second, or when t equals 1 second? So when we're asked questions like how high it is, well, we should be thinking, well, I need to plug that into the height equation. So I'm going to substitute those values into height there and see what I get. So h of 1/2, just throw it into the formula. Negative 16 times 1/2 squared plus 48 times 1/2 plus 64. Let's see, that's going to be 1/2 squared is 1/4. Negative 16 times 1/4 is -4. 48 times 1/2 is 24 plus 64. And I'm running out of room here. -4 plus 24 is 20. 20 plus 64 is 84. So after 1/2 a second, it went from when I threw it at a height of 64 feet to a height of 84 feet. So it gained 20 feet in height in 1/2 a second. Okay, let's look at how high it is after 1 second. 1 second is even easier. We're just going to plug in 1. H of 1 is going to be, let's see, negative 16 plus 48 plus 64. Negative 16 plus 48 is 32 plus 64 is 96. And it kind of makes sense that in this next 1/2 a second, it's covered less ground, right? You threw it up, but as soon as you throw it up, it starts slowing down, right? I threw it up at 48 feet per second, but right away it's going to be like, okay, well, I'm slowing down because gravity is having an effect on me. So, right, in the first 1/2 a second, it increased in height by 20 feet. In the next 1/2 a second, it went from 84 to 96 feet. It only went up another 12 feet. And every additional 1/2 a second we go up, it's going to gain less height because it is slowing down until it's going to top out. So the other question I want to ask about this is, what's the average velocity of the rock in this interval between time equal to 1/2 a second and time equal to 1 second? Well, we know how to find average velocity. It's displacement divided by how much time has elapsed. So that's just going to be the change in position over the change in time, which in this case is going to be 96 minus 84, right? Height of 96 minus the height of 84 feet over 1 second minus 1/2 a second. So that's going to be, let's see, 96 minus 84 is 12 over 1/2. That's going to be 24 feet per second. So between 1/2 a second and 1 second, it averaged a speed of 24 feet per second. Okay, that doesn't seem too unreasonable. Yeah, that makes sense to me. Does that make sense to you? I'm like, great, it makes sense to me. Sure, yeah, that makes sense. But then I would also like to talk about the actual instantaneous speed at each of those moments. So we can see that that's going to be given by the derivative, which is h prime of t. Right, so again, we've got this ball, this rock, that we've thrown off some building at a height, you know, and it's going up like this, and it's coming back down like this. And so in this first, you know, from 1/2 a second to 1 second, it's traveled some height over some time interval, but obviously we don't know the exact speeds yet because we haven't calculated what they are. We can see using the velocity equation that after 1/2 a second has elapsed, we're traveling at a speed of negative 32 times 1/2 plus 48, which is negative 16 plus 48, which is 32 feet per second. So at 1/2 a second, we're traveling at 32 feet per second. And similarly, if we plug in 1, we're going to get negative 32 plus 48, which is equal to 16 feet per second. So at 1/2 a second, we're traveling at 32 feet per second. At 1 second, we've definitely slowed down to 16 feet per second. It is a coincidence here that the average of those two is what we actually got for our average velocity. That is not always the case that you can just average the endpoints and get the actual velocity, but it usually does work out that way for quadratics because of how the derivative works. But I would say just don't fool yourself into thinking that, oh, I can just find the average by taking the two velocities at the end. And no, that's not quite how things work. So often the kinds of questions we ask with this setup is, how high does the rock go? Well, to answer that question, we have to know when it is at its highest point. So the rock is at its highest point well, on the picture, it's right there. And we can see that the rock is going up, but it's slowing down, right? Until right there, the velocity is 0. So the highest point is when the velocity, which is the derivative of position, is equal to 0. Which we can find by setting the velocity equation equal to 0. So then we'll set that equal to 0 and solve for t. So negative 32t equals negative 48. T is going to be negative 48 divided by negative 32. Those are both divisible by 16. That's going to be 3 over 2, or 1.5. That's not how high it is. That's just what time it is when it's the highest. To figure out how high that actually is, we have to plug that into the height equation. So the height at time equal to 3/2 is going to be negative 16 times 3/2 squared plus 48 times 3/2 plus 64. It's going to be negative 16 times 9/4 plus 48 times 3/2, I can cancel a 2 here and a 2 here. And 24 times 3 is 72 plus 64. Negative 16 times 9/4, I can cancel a 4 here and a 4 here. And negative 4 times 9 is negative 36. So I get negative 36 plus 72 plus 94. That gives me a positive 30. Oh, 94, 64. Positive 36 plus 64 is going to be 100. So that's how high the ball goes, 100 feet off the ground. The other kind of typical question that people often ask is, how fast is the ball going when it hits the ground? So again, we're asking for a quantity when a certain time is happening. So we first have to answer the when part. What time is it when the ball hits the ground? So just like the highest point is when the velocity is 0, the ball hits the ground is when the height is 0. So typically when they're asking, oh, when is this thing happening? It's usually when something is 0. So yes, the ball hits the ground when the height is 0. I should try not to use up my favorite pen all at once. So, notice this looks right. So, ball hits the ground when the height h of t, which is negative 16t squared plus 48t plus 64 is equal to 0. This pen does not look like it is looking so hot. Let me check this ending here real quick. Sorry. Going on, mouse. Why aren't you working? Okay, there we go. No, okay, we're good. Okay. So if someone's been thoughtful about this kind of question, they'll usually pick numbers that are multiples of 16 to make life easier. So I'm trying to set this equal to 0. I'm going to factor out a negative 16 because I can. Or you can divide both sides by negative 16. Same difference. 48 divided by negative 16 is minus 3t, and 64 divided by negative 16 is negative 4. And I can definitely factor this. This factors is t minus 4 times t plus 1. So the ball hits the ground when time is equal to 4 seconds, or when time is equal to negative 1 second. Obviously, negative 1 second doesn't really make sense, right? It's kind of the idea that, right, if you could imagine you were actually like going back in time, the ball, right, we would have started down there at negative 1 second, and then after 1 second, we'd be at when we actually started, which is a height of 64 feet, and then continuing on. So forth. I will also point out, right, parabola, the middle of your intercepts is when you get the vertex. The middle of 4 and negative 1 is positive 3/2, which is definitely where we found the highest point. So usual types of things are making sense here. So hits the ground. I know it looks like kind of like 45. That is 4 seconds. Maybe I should erase the S. My S's always look like 5s. So 4 seconds is when it hits the ground. And then we want to find out how fast it's going when it hits the ground. So we're going to plug in 4 into the velocity equation. So v of 4 is equal to negative 32 times 4 plus 40, which is going to be something. Negative 32 times 4 is negative 128 plus 48, which in this case is negative 80 feet per second. So when the ball or the rock hits the ground, it's traveling at 80 feet per second, but it's traveling downwards. So we say it's negative 80 feet per second, because usually, not always, but usually, we envision the upward direction as being positive velocity and the downward direction as being negative velocity. You don't have to do it that way, but it's pretty typical. Let's see. Sure. Let's do, yeah. We can do another one later if we have time. But I feel like I just dropped my pens all over the place. I feel like we should get back. We should move back towards all these derivative rules we've got. So I'm going to remind everyone of the trig derivatives because we should be reminded of them. But I really want to emphasize, you should memorize the trig derivatives. They are definitely going to come up all the time in Calc 21A, 21B, 21C, like the trig derivatives are going to be with you forever. So you might as well take some time, memorize them. And I definitely encourage you to memorize them in the way I'm going to write them. So I'll remind you, the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x. And the reason I like to write them this way is because sine divided by cosine is equal to tangent. I will also point out, it's definitely not true that cosine divided by negative sine isn't secant squared. So it definitely works for this first part, but you can't say the derivative of the quotient of two things is equal to the quotient of their derivatives, right? Derivative of this divided by this is not equal to the derivatives equal to each other. Okay. But definitely sine over cosine is tangent. And then we write the reciprocals next to them. The reciprocal of sine is cosecant. The reciprocal of reciprocal of cosine is secant. And the reciprocal of tangent is cotangent. The derivative of cosecant is negative cosecant x cotangent x. The derivative of secant x is secant x times tangent of x. And the derivative of cotangent of x is negative cosecant squared of x. A couple things to remember. All the cofunctions have negative signs on the derivatives. Cosine, cosecant, cotangent all have a negative on their derivative. Furthermore, I want to really stress the derivative of secant of x is secant of x times tangent of x. There are two x's there. It's not secant tangent x. It's secant of x times tangent of x. Similarly, the derivative of cosecant of x is negative cosecant of x times cotangent of x. Just want to point that out. So those are the trig derivatives. Memorize them. You definitely want to memorize them. Let me say it again. Memorize them. Okay, so they're mesmerizing, so memorize them. There is a really good, there are actually like two really good reasons to memorize them in this order. One of them being that if we talk about the hyperbolic trig functions, which aren't really trig functions, but act very similar to trig functions, it's really nice to write them in the same order because there's some nice patterns that come out. Also, I think that's about it. This is just a nice way of writing. So I would recommend doing it this way. So let's do a couple more derivatives involving the various power, product, chain, and quotient rules. So let's see, let me scroll down a little bit here. Yeah. And so let's start with a couple not too terrible examples. Like let's say our function is, what have I got here? Sure. X to the 10th plus, oh, I don't think we've done that yet. Cosine of 2x to the 6th. So there's a function. I'm definitely going to have to use the chain rule because I've got some stuff to the 6th power. So my derivative here. So here's the way I really think about it. I think about first, what's the outermost function? The outermost, and I saw someone do this a little differently on the quiz. That is fine if you do it differently. I definitely saw someone work from the inside out, which I thought was kind of cool. Not gonna lie, I'm always interested in seeing new ways of thinking of things. But what did I want to say here? There was something, and now I've totally lost my way. But I typically think of it from the outside in. So I'm going to say, all right, I've got some stuff to the 6th power. And I know that x to the 6th has a derivative of the 6x to the 5th. So some stuff to the 5th, sorry, some stuff to the 6th has a derivative that is 6 times my stuff to the 5th power. And I have to multiply by the derivative of that stuff. So 6 times my stuff unaltered. But then I have to multiply by the derivative of that stuff. And you can either, some people like to write, some people like to write, sorry, I don't know the answer to the question that's being asked to me in the chat privately. I don't think it's, so let me double check one thing real quick here. Sometimes I have things open that make my screen blurry for you guys. Hopefully it's not blurry for many of you. I don't think I have anything crazy open. Yeah, sorry, one sec. Yeah, I've closed all the things that might possibly be interfering. I apologize to those of you that are maybe having issues seeing things. I will say, I will upload the video later, and it might be easy to see, but I'll try and say the things very clearly. So here's what we've got so far. We've got 6 times x to the 10th plus cosine of 2x to the 5th. And then we're going to multiply by the derivative of x to the 10th plus cosine of 2x. The derivative of x to the 10th is straightforward. It's 10x to the 9th. The derivative of cosine of 2x, we actually have to be a little bit more careful. So for x to the, for 10x to the 9th, or sorry, for cosine of 2x, we actually have to use the chain rule again. The derivative of cosine of x is negative sine of x. The derivative of cosine of 2x is negative sine of my stuff, which is 2x. But I have to multiply by the derivative of 2x, which is 2. And I could probably justify leaving it like that, but I could also do a tiny simplification and write it as 6 times x to the 10th plus cosine of 2x to the 5th times, I would rewrite this as 10x to the 9th minus, I put the 2 in front, 2 sine of 2x. And that's how I would do that one. Let's look at a couple more. Oh, I know what I want to talk about specifically.
Wait, why do you have to take the derivative of cosine 2x again? Why do you have to take the derivative of cosine 2x again?
Well, it's not that I took the derivative of it again. I only took its derivative once, right here. So the derivative of cosine of 2x is negative sine of 2x times 2. I think the question, and I'm not exact sure, but it sounds like the question you might really be asking more is, why do I have to multiply by the 2 here? It's because when I take the derivative of cosine of 2x, I have to use the chain rule again. The derivative of cosine of a thing is the derivative of the outer function, and the derivative of cosine is negative sine. So the derivative of cosine of a thing is negative sine of that thing, which is 2x. I have to multiply by the derivative of 2x, which is 2. Right there. Hopefully
okay. Yeah.
Sorry, did you have more to say?
Oh, no, that's it. Thank you.
Cool. All right, let's look at some more examples. Really, I definitely recommend, if you want more practice, I really recommend looking at that derivative worksheet that I posted on campus. I think it's got a lot of good problems, and the answers are all there. So let's look at another example, like f of x equal to the square root of tangent of x plus x cubed. For this one, I really want to rewrite it. I want to rewrite it as tangent of x plus x cubed all to the 1/2 power. So that now I can use the power rule. I've got some stuff to the 1/2 power. My derivative is going to be, well, again, I know what the derivative of something to the 1/2 power is. It's 1/2 times my something to the negative 1/2. Just like the derivative of x to the 1/2 is 1/2 times x to the negative 1/2. So it's 1/2 times my stuff to the negative 1/2. But then, right, if I'm saying stuff, which is why I say stuff, I know I'm going to have to multiply by the derivative of my stuff. So here I'm going to get tangent of x plus x cubed. And then I have to multiply by the derivative of that, which I'm going to write just slightly wrong, and then we're going to fix it. Derivative of tangent of x is secant squared of x. Derivative of x cubed is 3x squared. If you write it like this, you're going to lose a point, at least if you're in my class, because it's 1/2 times my stuff to the negative 1/2 times the derivative of all the stuff. But if you write it like this, it looks like I'm just multiplying by secant squared x, and then after I multiply, I'm adding on the 3x squared. I have to put parentheses around the derivative of my stuff if there's more than one thing being added or subtracted together. All right. So let's look at another one. I think I can fit it here. Let's look at, say, g of x equal to 3 over secant of x plus 7. We have options here. We could totally rewrite this so that we don't have to use the quotient rule. We could use the quotient rule. I don't really want to use the quotient rule, especially since my numerator is a constant. If it was maybe something more complicated on top, I would probably use the quotient rule. But here, I'm going to rewrite this as 3 times secant of x plus 7 to the negative 1. And I'm going to take the derivative as, so I'm going to say this now, and I'm going to do another example in a minute here. When you take the derivative of a constant times a function, the constant just sticks around. I'm going to get 3 times the derivative of this to the negative 1 power. The derivative of something to the negative 1 is negative 1 times my something to the negative 2. The to something being secant of x plus 7. But then I have to multiply by the derivative of the insides, which is the derivative of secant x is secant x times tangent x, plus the derivative of 7 is 0. So you get the secant x times the tangent x. You really want to stress when you have a constant multiple and you differentiate, the constant multiple sticks around and multiplies the derivative. When you have a constant that's added or subtracted and there isn't any variable that's multiplied by it, its derivative is just 0. But I want to make sure that people are really clear about that. Let me show you with another example. Something I want to make extra clear. So I'm going to do, let's take the derivative. We're going to do something moderately easy. Let's take the derivative of, sorry, I'm trying to think of something that seems not too silly here. Let's do 4 times x to the 5th. Now, we are going to do this very easily, and then we're going to do a little bit more work to kind of see what's happening here. Take the derivative of 4 times x to the 5th. One way of doing it is just saying, oh, it's 4 times the derivative of x to the 5th, which is 4 times 5x to the 4th, which is 20x to the 4th. Which seems like a lot of work. Really, I know most of you just be like, oh yeah, 5 times 4 is 20, 1 less power is 20x to the 4th. What I want to point out here is that some people sometimes are like, well, isn't the derivative of 4 0? And it is, right? The derivative of 4 is 0. But the problem here is I've got 4 times a thing. Another way to think of this, if you want to justify yourself, why am I thinking there should be a 0 here? Well, it's because you could, if you wanted to, use the product rule. You can say, okay, it's going to be the derivative of 4, which is 0, times x to the 5th, plus 4 times the derivative of x to the 5th. But the derivative of 4 is 0. So you get 0 times x to the 5th, plus 4 times the derivative of x to the 5th, which is 5x to the 4th. So you get 0 plus 20x to the 4th. So what I'm trying to say here is you can totally use the product rule if you've got the derivative of a constant times a function, but you don't really need to. You can say, oh, the derivative of a constant times a function is just the constant times the derivative. If you want, you could also go the product rule route, but you don't have to. Another way to think about this is say I've got the derivative of, I don't know, sure, 5 times cosine of x, just to make it again very kind of straightforward. We could use the product rule. I don't want to use the product rule. I want to say I know the derivative of 5 times cosine of x is 5 times the derivative of cosine of x, which is 5 times the negative sine of x, which I would write as negative 5 times sine of x. But we want to be absolutely clear, right? Whereas on the other hand, if someone said, what's the derivative of 5 plus cosine of x, then the derivative there, derivative of 5 is 0, and the derivative of cosine is negative sine of x, which is just negative sine of x. So I want to be very emphatic. Constants that are not multiplied by any variables, their derivative is 0. Constants that are multiplied by variables, I like to think of them as hanging out when you take the derivative. At the derivative of a constant times a function, the constant hangs out, and you multiply it by the derivative of the function. So hopefully that clarifies things fairly well. Let's look at a few more examples. There was definitely one like this that we did at the end of last class, and I also put one like this on the quiz, where you have a trig function to a power, like say the derivative of cotangent to the 6th power of x to the 7th plus e to the x. Oh, have we done the derivative of e to the x? I can't remember. Yes, no, maybe so. All right, I'm not hearing any no's. Okay, I'm sorry, it's hard to remember all the derivatives that we've covered, but I feel like we've done e to the x. All right, well, here it is anyway. So before we differentiate this, we should rewrite it. You don't have to rewrite it. I like to rewrite it. I want to write this as cotangent of x to the 7th plus e to the x to the 6th power. So that's very, very obvious to me that the outermost function is being raised to the 6th power. So then I'm going to take the derivative. I've got some stuff to the 6th. We've already taken the derivative of some stuff to the 6th. It's 6 times my stuff to the 5th. So it's going to be 6 times all my stuff to the 5th power. But then we have to multiply by the derivative of the stuff. I know, I want to emphasize everything. I really want to emphasize. I want to point out that when you take the derivative of the outer function, the inside function has to stay the same. Right? So the derivative of something to the 6th power is 6 times that same something to the 5th power. But then we have to multiply by the derivative of that. Well, the derivative cotangent of a new thing, right, because I'm going to use the chain rule again. Derivative cotangent of a new thing is negative cosecant squared of the new thing times the derivative of that new thing. Okay. So it's going to be negative cosecant squared of x to the 7th plus e to the x. Then I have to multiply by the derivative of x to the 7th plus e to the x, which is 7x to the 6th plus the derivative of the x to the x. And so this here is my stuff, right? I'm taking the derivative of some stuff to the 6th power, and the derivative is 6 times my stuff to the 5th times the derivative of my stuff, where the derivative of my stuff, I have to use the chain rule again, right? The derivative of cotangent of x to the 7th plus e to the x is negative cosecant squared of some new stuff times the derivative of that new stuff. Let's look at another one. And then, yeah, and then we'll, I think after one or two more examples, we'll start talking about implicit. Maybe.
So the trick is to recognize the outermost function?
For sure. Yes, exactly.
Okay.
And yeah. And it's really, I mean, most of the time it's not too hard to tell what it is. The kind of the times where it can be the most challenging is often when you have a trig function to a power, because kind of we think of like the thing that we read first is often the outermost thing. That's not really true when you have a power on a trig function like that. So yeah, for example, another example like that, if we had something like y equal to secant to the 4th of x squared times sine of x. And again, since I've got a trig function to a power, I'm going to rewrite it so it's a little more obvious. I've got secant squared, secant of x squared times sine of x all to the 4th power. So then after I've written it that way, I can really, really see, oh yeah, being raised to the 4th power is my quote unquote outermost function. And so when I start taking my derivative here, dy dx, it's going to be that stuff to the 4th. The derivative is going to be 4 times that stuff to the 3rd times the derivative of some stuff. And then I'm going to leave myself some extra here. So we get 4 times secant of x squared times sine of x. Oh yeah. To the 3rd, all times the derivative of secant of x squared times sine of x. All right, and I definitely wrote it in the way that I'm going to have to do more work. I'm going to have to write it again. So this is going to be 4 times secant of x squared times sine of x, all to the 3rd, times, okay, this is definitely one that threw a few people on the quiz. The derivative of secant of some stuff is secant of that stuff times tangent of that stuff. So it's going to be secant of x squared times sine of x times tangent of x squared times sine of x times the derivative of the stuff. The derivative of x squared times sine of x. So then I have to do one more step. We could have done the derivative of x squared times sine of x there, but I wanted to write out one more step because I'm a glutton for punishment. If you want to, at this point, you can start changing things back, right? You will often see people simplify. So first of all, this is 4 times secant cubed of x squared sine of x times another secant of x squared times sine of x. You could compress that down to 4 times secant to the 4th of x squared times sine of x. Right, that is, this here is all of this. If you want to combine it all in a, and you do, I mean, right, if it's not hard to see the simplification, it's a lot less writing. But we've got the tangent, which we can't combine, and we've just got tangent of x squared sine of x. And then finally, the derivative of x squared times sine of x, we have to use the product rule and get the derivative of x squared, which is 2x times sine of x plus x squared times cosine of x. Okay. One kind of pitfall to avoid that I definitely saw a little bit on the quiz. If I ask you to take the derivative of, say, like sine of x to the 5th, it's not a product rule question, right? The difference between, so this is not the same as the derivative of sine of x times x to the 5th. Right? That's a very for sure product rule because it's a function times another function. But here this is a chain rule because it's a function of another function. That's why I really try and stress the language of the math because it's really important to say the right things. If you say sine of x to the 5th, like the of is a reminder that, oh, I have a composition of function. I'm taking a function of a function. Whereas here it's sine of x times x to the 5th. So it's much more obvious that this is a product rule and this is a chain rule. Okay. Let's see. Let me do one more kind of, yeah. Oh, yeah, couple more. Like, what's the derivative of e to the, ooh, let's make it fun. Let's do x squared over, sure. Tangent of x. Something I would definitely recommend here. I don't love using the quotient rule unless I have to. And in this case, you could definitely rewrite this as the derivative of e to the x squared. Instead of dividing by tangent, we can multiply by the reciprocal of tangent, which is cotangent. So you can say this is the derivative of e to the x squared times cotangent of x. So at least we don't have to use the quotient. We already have to use the product rule. But before we can do either, what's the derivative of e to the stuff? I don't ever actually say that. I'm really asking, what's the derivative of e to the x? Oh, it's e to the x, right? The derivative of e to the x is its own derivative. It's e to the x. There's only one other kind of function that's its own derivative, and that's 0. The derivative of 0 is 0. Otherwise, it's e to the x. So the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the what?
Derivative of the stuff.
Exactly. That's like, oh, if I'm saying the derivative of something and I say the word derivative of stuff, the answer is the derivative of stuff. I was talking with my coworker the other day about like we call this the exponent, but there's no good name for like just being in the not exponent or not, right? There's like the exponent, there's the denominator, there's inside a function, but there's no good, like, at least I couldn't come up with any good words for just being like in the regular place where you're not inside something else. So yes, you get e to the stuff times the derivative of the stuff not in the exponent, right? You're outside the exponent. So it's the e to the stuff, which is x squared times cotangent, times, I'm not in the exponent, the derivative of that stuff, which again, we got a product rule going on. So it's 2x times cotangent of x plus x squared times the derivative of cotangent, which is negative cosecant squared x. So there's our answer. You could probably rewrite it a little bit if you wanted as e to the x squared times cotangent of x times the quantity 2x cotangent x minus x squared times cosecant squared of x, if you want to bring that minus sign out in front of the x squared. Okay, one more chain rule, and then I guess we'll take a little break, and then we'll come back and we'll start talking about the quotient, not the quotient, the implicit stuff. Where'd you go? Example? Oh, yeah, let's do this one. Let's look at. We'll make this one. Well, yeah, we'll end with a gross one. All these quotes. So I'm trying to give you guys derivative problems that are kind of extra gross, because it's good to practice the hard stuff. So that then when you see the hard stuff, it's not so hard, and then the less hard stuff seems super easy. So let's look at, say, let's look at f of x equal to, and this is also similar to a quiz question he gave you guys. Also, I should mention, Brett, the quiz solutions are posted. I will always try and get them posted. Sometimes I post them before the quiz is even due. Again, I don't recommend just copying out the answers, because what's the point? But you're always welcome to look at the solutions once they're posted, and I think you should definitely look at them if you have questions about how the quiz works. So let's do the derivative of some terrible quotient like, how terrible do I want to make this? Let's go that way. Let's go cosecant of x plus 2 all over, I'm going to make it real fun, sine of 3x plus x to the 9th power. So people did this problem different ways, which is fine. A lot of people distributed the 9th or whatever the power was first, and then did the derivative using the quotient rule. And that is perfectly legit. So you can still say like, I've got cosine x plus 2 to the 9th over sine of 3x plus x to the 9th, and then do the bottom times the top minus the top times the bottom all the bottom squared. I think it's a little less work, really, to do the chain rule part first and the quotient rule part second. So if I'm going to do the derivative, I'm going to think of it this way. Although I can certainly show the other way if you guys want me to. I'm going to think of it as 9 times my stuff to the 8th power times the derivative of that stuff. So it's 9 times cosecant x plus 2 over sine of 3x plus x to the 8th times the derivative of that inside part. Which is a perfectly fine way of doing it. I think doing it this way, if you were asked to simplify at the end, it is a little easier to simplify this than it is to simplify it doing the other way. Maybe not, but it could be. No, I think I don't know. Anyway, I did do the simplifying on in the quiz. You can see all the simplification there. It's kind of a pain, but no big deal. So this is 9 times cosecant x plus 2 over sine of 3x plus x to the 8th power. And then we're going to do the derivative of this, which again, it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Or as I actually say, it's the bottom times the derivative of the top. So the bottom is sine of 3x plus x. And since there's more than one thing, I have to put that in parentheses because I'm going to multiply it by the derivative of the top, which is derivative cosecant x is negative cosecant x cotangent x. So times negative cosecant x cotangent x. And the reason I'm putting parentheses there is because if I write times negative, it just seems weird. I need parentheses. Minus the top cosecant of x plus 2 times the derivative of the bottom. The derivative sine of 3x, we have to use the chain rule here. Your sine of some stuff is cosine of the stuff times the derivative of the stuff. So the derivative sine of 3x is cosine of 3x times the derivative of 3x, which is 3. So it's cosine of 3x times 3 plus the derivative of x, which is 1. over the denominator squared. And I would leave it like that. But I will point out that if you wanted to simplify this a little bit, not a lot, just a little bit, one thing people commonly do is they do say, oh, it's really the top, which is cosecant of x plus 2 to the 8th power, times all of this not multiplied out. And then the bottom is sine of 3x plus x to the 8th times sine of 3x plus x to the 2nd, which becomes sine of 3x plus x to the 10th. So a lot of times with these kind of problems, when you see that the denominators are essentially the same, but to different powers, we multiply the denominators together and add the powers because it's kind of nice. Yeah, which you don't really see if you do with the other. That's fine. All right, let's look at this. So here's the question I actually want to find. So find all x values where f of x has a horizontal tangent line. And when I say a horizontal tangent line, what you should be hearing is, oh, he wants me to find all the places where the derivative is equal to 0. Because that's what it means to have a horizontal tangent line, right? It means the slope of our tangent line, also known as the derivative, is 0 because the horizontal line has a slope of 0. So here's my function. My function is f of x is equal to, what do I got here? 2x plus 1 to the 6th times 5x minus 3 to the 4th. And although this is completely unnecessary, I'm going to do something that's going to kind of help drive home the idea of this being implicit. Yeah, no, maybe not actually. I think I'll do that after. So let's say, so I want to take the derivative of this, right? So the derivative is going to be, let's see. So I'm going to use the product, or I'm also going to use the chain rule, right? Because, so I'm thinking of this, right? I've got two pieces multiplied together, which I might call like u and v. And the derivative is going to be u prime v plus u times v prime, where u and v are both functions of x. So to take the derivative of u, I'm going to have to use the chain rule, which is the derivative of some stuff to the 6th power is 6 times my stuff to the 5th power times v, which is 5x minus 3 to the 4th, plus u, which is 2x plus 1 to the 6th, times the derivative of v, which again, chain rule. Oh, I made a mistake. Hopefully before there's something missing over here, which I'll let you guys think about for a second while I finish off this. It's going to be 4 times 5x minus 3 to the 3rd. Well, if I say what I'm missing here, I'll probably get away with this over there. Times 5.
Derivative of the inside.
Right. So just like here, I had to multiply by the derivative of the inside, which is the derivative of 5x minus 3, which is 5. Over here, I should have been multiplying by what?
2.
Exactly. And so here's the thing. A lot of the time, if I said just find the derivative of this, we would probably leave it here. But now since we're trying to find where the derivative is equal to 0, this is when we really want to simplify. Specifically here, I really want to factor. So I'm going to say, okay, well, I can factor out what? Well, I've got a 2x plus 1 to the 5th and 2x plus 1 to the 6th. So I can definitely factor out a 2x plus 1 to the 5th, because I got 5 of them there and 6 of them there. In a similar way, I could factor out a 5x minus 3 to the 3rd, because I got 3 of them there and 4 of them there. Essentially, if you've got things added together and the same factors to different powers, you can always factor out the lesser power amount, even if that lesser power is a more negative power. So then I can probably factor out some multiple of 4 or something. I'm not going to worry about that right now. So let's see. If I factor that out, I've got a 6 times a 2 times a 5x minus 3. And that's what's left from here. And over here, I've got a 4 times a 5 times a 2x plus 1. That's what I get from right there. And I want that to be equal to 0. So let's see. I'm going to get 2x plus 1 cubed times 5x, sorry, 2x plus 1 to the 5th, sorry, times 5x minus 3 to the 3rd, times, well, let's see. So this is 12. 12 times 5x is 60x minus 36 plus 20 times 2x is 40x, and 20 times 1 is 20. So simplifying just a tad, I've got 2x plus 1 to the 5th times 5x minus 3 to the 3rd times 60x plus 40x is 100x minus 36 plus 20 is minus 16. So then we're going to set each of the 3 factors equal to, so here's what usually happens with this. A lot of people find that negative 1/2 is a solution and positive 3/5 is a solution, but they don't get the last solution, which is from this factor here. So we're going to get that right from this one, 2x plus 1 equals 0, which means x equals negative 1/2. 5x minus 3 equals 0, which means x equals positive 3/5. And 100x minus 16 equals 0, which means x equals positive 16 over 100, which reduces to 8 over 50, which reduces to 4 over 25. Or 0.16 if you prefer a fraction. I mean a decimal. Okay. And the parallel I wanted to make to implicit is not as good as I thought it might be there. So let's move on.
So when finding the zeros, we don't have to think about the powers that.
No, you don't, exactly. So when you're trying to find the zeros of a derivative, you're basically just trying, really I'm setting each factor equal to 0. So what I'm really doing, right, is I'm setting 2x plus 1 to the 5th equal to 0. And then you can either take the 5th root of both sides or just say the only way something to the 5th is 0 is if the insides are 0. So then we're like, oh yeah, 2x plus 1 equals 0. And then x equals negative 1/2. But yeah, I'm not really worrying about the powers. The exception there is if the powers are negative. Right? If you factor this and you end up with like a 5x minus 3 to the negative 2nd power, then you don't want that to be 0, because 0 to a negative power is really division by 0, which is undefined. So just be a little careful there. Excuse me. So let's say we have this function. Y equal to, and it's not going to be super terrible, x cubed plus 1 to the 10th plus sine of x plus 2 to the 8th plus x to the 5th. And for reasons that will become clear shortly, maybe, dropping stuff, sorry. I'm going to rewrite this using other letters just for a minute. I'm going to call this inside part here U, and this inside part here W. So that I can rewrite this more simply as U to the 10th plus W to the 8th plus x to the 5th. And now I'm going to differentiate, but I want to be really, really clear. Everything's still a function of x. It's just that I happen to write these other letters in, which are also functions of x. So what I can say is, even though it's not written here, right, U and W are implicitly functions of x. So when I take the derivative with respect to x, well, what's the derivative of some stuff to the 10th power? It's 10 times my stuff to the 9th power times the derivative of my stuff. And similarly, the derivative of w to the 8th is 8 times my stuff to the 7th power times the derivative of my stuff, which is dw dx. But then the derivative of x to the 5th, x is the variable I'm differentiating with respect to, so I don't have to be all complicated about it. The derivative of x to the 5th is just 5x to the 4th. But now we're going to go back. We're going to say, well, I really want my answer to actually just have x's in it. Or like I would love for my derivative, if possible. It's not always going to be possible. And sometimes our answer, we're stuck with these other things. I would love for my actual function to have the original variable. So I can plug back in and say, oh, u is actually just x cubed plus 1. This is 10 times x cubed plus 1 to the 9th times my du dx, which is just the derivative of this, which is 3x squared. Plus, I could plug back in that w is sine of x plus 2. Get 8 times sine of x plus 2 to the 7th times dw dx. dw dx is the derivative of this with respect to x, which is just cosine of x, plus the derivative of this, which is 5x, or sorry, not which is 5x. Or you could just say, I took a really long trip to do the chain rule, right? This is just the chain rule. The derivative of some stuff to the 10th is 10 times my stuff to the 9th times the derivative of my stuff. The derivative of some stuff to the 8th is 8 times stuff to the 7th times the derivative of my stuff. Derivative of x to the 5th is 5x to the 4th. Okay? But the idea here is important. And the idea here is that if you have something that you know is a function of x, even if it's not written as a function of x, we treat it like it's a chain rule kind of thing. Say, oh, this function of x to the 10th power is 10 times that function of x to the 9th power times the derivative of that function of x, just like the chain rule would have us do. Well, that's for a reason. And so what I really want to say is that just the chain, the implicit differentiation is really just the chain rule. Like, no joke. It's just that it's the chain rule with a little bit of extra algebra to do afterwards. So let's look at a very, very straightforward example, I think. Let's find the slope of the circle. Actually, let's say the slope of the tangent line, of the line tangent to the circle, x squared plus y squared equals 25 at the point, let's go 3, -4. So here's my circle. And maybe, yeah, sure. There's the point 3, -4. I feel like I've gone, yeah, maybe I've gone a little too far out. It's okay, it doesn't really matter. Now I want to find the slope of that tangent line. Okay, one way we could do it would be to solve for y and take the derivative. It's perfectly fine if you can do it. You can't always do it, which is why we're talking about implicit. But I can totally solve for y squared equals 25 minus x squared. Take the square root of both sides. Now I'm gonna, sure, y is equal to the square root of 25 minus x squared. Well, not really, actually. So one of the problems with solving for y here is that you have to be kind of more careful than I really like to have to be. Y is actually the plus or minus square root of 25 minus x squared. And this top part, right, this part here, this is the plus part. And this bottom part here, that's the minus part. So to even be able to take the derivative at this point, I need to know that that point is on the bottom part, which is the negative part. Kind of more work than I'd like to do. Okay, fine. So really I'm looking at y equal to negative 25 minus x squared to the negative 1/2, positive 1/2, sorry. And now I'm going to differentiate. So my derivative, dy dx, is equal to, okay, so I'm using the chain rule. The derivative of minus stuff to the 1/2 is minus 1/2 times my stuff to the new power is -1/2. Leave the inside stuff alone. Multiply by the derivative of the inside stuff, which is -2x. And we could simplify that a little bit. The -2 and the -1/2 cancel out. So I end up with the derivative equal to x times 25 minus x squared to the -1/2. Or if you prefer, x over the square root of 25 minus x squared. So then we could plug in x equal to 3 and get that if x equals 3, the derivative is equal to 3 over the square root of 25 minus 9, which is 3 over 4. Which seems sensible in that, okay, yeah, that slope looks like it's positive. I definitely got a positive slope. Great. That's a lot of work. More importantly, it's more work than I have to do. There's a much, much, much easier way to do this. And I wish I had room on this side of the board so I could write on this side, but I can't. So instead, we're going to do this. Now, one of the reasons it's called implicit differentiation is because when you write this equation, x squared plus y squared equals 25, it is implied, but we can't really find explicitly, that y is a function of x. Y technically is not a function of x, but y certainly depends on x, right? Y is equal to plus or minus the square root of 25 minus x squared. So when you know x, you have a very, very good idea of what y might be.
So more simply, the relationship between y and x is implicit?
It's
that not right?
I think there's a couple of reasons. One of the reasons is often because we cannot solve for y explicitly. So the functional relationship, the fact that y isn't actually a function of x, but we are implying that it acts like a function of x, essentially, is what's going on.
Cool.
And we're definitely going to treat it like it's a function of x. So let's go back to our original x squared plus y squared equals 25. And we're saying, hey, y is a function of x. Just like in that previous problem, w and u were functions of x. So when I take the derivative here, or if I differentiate, remember, y is a function of x. The derivative of x squared is 2x, but the derivative of y squared, or some stuff squared, is 2 times my stuff to the first power times the derivative of that stuff, which I'm going to write as dy dx, even though I'm usually going to write as y prime, equal to the derivative of the other side, which is 0. I want to make sure everyone's okay with this, because this is kind of really big, the important part, right? We're thinking of y as a function of x. So that if our function is squared, the derivative of y squared is 2 times my stuff times the derivative of that function of x, or times the derivative of that stuff. Just like all the other chain rule things we've done. Okay, but now we're going to solve for dy dx, because we're being asked, just like in the previous same problem, what's the derivative? Well, it's right there. I'm going to solve for it. So I've got 2y times dy dx equal to -2x, and then divide both sides by 2y, so that dy dx equals -2x over 2y. The 2's cancel, so dy dx equals -x over y. And now look, if we plug in the point 3, -4, we get that the derivative is, so we can write, I'm going to write it this way. So dy dx evaluated at 3, -4 is equal to -3 over -4, which is 3/4, just like it was before. The difference here is that here we had to plug in the x and the y value because there was a place for the x and the y value. I will also point out that in this example, since we were able to solve for y explicitly, you could rewrite this as negative x over y, where y was the negative square root of 25 minus x squared. And see that, oh yeah, you do actually get the same result. You still get x over the square root of 25 minus x squared. So when you can solve for y explicitly, whether or not you do it explicitly or implicitly, you should get to the same result. Yeah, your result might look different because you might have x's and y's instead of just x's, but it's still the same thing. But we're going to see a lot of examples where we cannot solve for y explicitly.
Can we also do a second derivative of an implicit function?
Yes, but it is a little bit challenging. But we can definitely talk about that after we do some examples of the first derivative. So this is the next example is very standard. It's probably in your textbook, but it is a nice example because it's one that's relatively easy to actually graph. This is called the folium of Descartes. And the equation is x cubed plus y cubed plus equal to 6xy. So here is an equation. We can definitely graph, well, we normally can't definitely graph, we can graph this one. I will show you what it looks like. Looks kind of like this. And it goes to the point 0, 0, because if x is 0 and y is 0, both sides are 0. It also goes to the point 3, 3. Because if x is 3 and y is 3, this side's 54 and that side's 54 as well. But you can't solve for y here, right? You can't get y in terms of just x. So the questions I would like to ask are a couple questions, actually. I would love to know, one, what's the slope there? And two, what's the highest point on this curvy part? It's not 3, 3. There's actually a point like right there that's a little bit higher. And so to find either of those things, I really need to know the derivative. So what's the derivative? Well, again, even though y isn't technically a function of x, we are going to treat it like it is. So we're going to differentiate both sides. So again, I should say we're going to differentiate both sides with respect to x. So the derivative of x cubed is 3x squared. The derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. Let's move to the right side. So I see a product, and here's what I would usually do. If I've got a product of a couple things and there's a constant multiple, I usually like to think of that constant as kind of living with really living with what's next to it. So I'm thinking of this as the product of 6x times y. I think it's just easier to see it that way. So then I'm going to do the product rule. The derivative of 6x is 6 times y left alone. Plus, and here's where the language is really helpful, 6x left alone times the derivative of y. What's the derivative of y? Oh, it's the derivative of y. You can also say it's 1 times y prime. So a lot of times what people do is they're like, oh, they take the derivative and then they multiply by y prime. So like the derivative of y cubed is 3y squared times y prime. The derivative of y is 1 times y prime. But you can also say the derivative of y is just the derivative of y, right? It's the derivative of y. Oh, it's the derivative of y. There's the derivative of y. It's dy dx. It's y prime, whatever you want to call it. Okay, and then after you've done this first step where you take the derivative of both sides, well, I should point out here, let me see one thing. Technically, if we really wanted to, we could just plug in 3, 3 right now and solve for dy dx. Most of the time, people actually do that. Well, I always say a lot of the time people solve first. I know here, since I'm going to ask another question about the derivative, it makes sense to solve for dy dx algebraically. So I want to solve for this. So the process here is almost always the same. We're always going to bring all the dy dx's or y primes to one side and all the other terms to the other side, factor it out, divide it with left over. So here, let's bring it all to the left. I've got 3y squared dy dx minus 6x times dy dx equal to 6y minus 3x squared. And then factor out the dy dx. So it's dy dx times 3y squared minus 6x equal to 6y minus 3x squared. And finally divide by this. So the dy dx equals 6y minus 3x squared over 3y squared minus 6x. In this specific example, you can go one step further and factor out a 3 from the top and a 3 from the bottom and cancel them. It's not particularly important, but it is something people often do. So then I want to answer two questions. Question one, what's the slope at that point? Well, that's easy enough. I can just plug in the point. So often you will see your teachers write it as derivative vertical line point at the bottom of the vertical line. dy dx evaluated at the point 3, 3. I'm just going to plug in 3 for x and 3 for y. I get 6 times 3 minus 3 times 3 squared over 3 times 3 squared minus 6 times 3. We could calculate this, but we can also just see it's the same thing on top as on the bottom, but subtracted in the opposite order, which means it's -1. Or you can say, oh, it's 18 minus 27 over 27 minus 18. That's -9 over 9, which is -1. So this tangent line has a slope of -1. Great. The other question we wanted to answer, that I want to answer, is where is this highest point in the curvy part, or in the loop? Well, to find the highest point, to find the relative maximum, you're going to find where the tangent line is horizontal, aka where the derivative is equal to 0. Excuse me. So we're going to solve for that derivative. I'm going to erase the picture because I'm going to erase the picture. So I want to solve this. I want to solve 6y minus 3x squared over 3y squared minus 6x equal to 0. And so when you want to solve a fraction equal to 0, you're really trying to solve the top equal to 0. So I'm trying to solve 6y minus 3x squared equal to 0. I feel like there's something I'm forgetting, so I should go back and make sure I don't do something dumb. Oh yeah, that's it. Okay. So then I'm going to solve for y. So I have 6y equal to 3x squared. I have y equal to 1/2 x squared. The problem is there's a lot of solutions to this equation. 0, 0 would be a point, and I know I just erased the picture, but definitely 0, 0 wasn't the point I was looking for. All right, the point I was looking for, right, was like somewhere here where x and y are definitely both positive. So how do I find the point on the graph if I only know that this has to be true to make the derivative 0? Well, I plug this back into the original equation. Right, this equation is x cubed plus y cubed equal to 6xy. So I'm going to plug this in for y and then try and solve for x. So let's see, if I do that, I get x cubed plus 1/2 x squared cubed equal to 6x times 1/2 x squared. That looks fun. Let's see what we get here. So I got x cubed plus 1/2 cubed is 1/8. X squared cubed is x to the 6th equal to 6 times 1/2 is 3. X times x squared is x cubed. So bringing everything to the left, I've got 1/8 x to the 6th. X cubed minus 3x cubed is minus 2x squared equals 0. And then I can factor out x squared, 1/8 x squared. I'm left with an x to the fourth minus 16. So either x is 0, which is actually this point here where there's a horizontal tangent line as well. There's also a vertical tangent line there, which is weird. Or x to the fourth minus 16 equals 0, which means x to the fourth equals 16, or x equals the fourth root 16. I feel like I made a crazy mistake here. It definitely made a mistake, because the fourth root of 16 is 2. And although it would be super nice if that was 2, it's not 2. So where did I make a mistake? Made a mistake right there. I subtracted and my power changed from 3 to 2 somehow. So that should actually be a third power, which means I should actually be able to factor out an x cubed, which means I'm actually left with an x to the third, not an x to the fourth. Sorry about that. Which means my answer is actually the cube root of 16, which is definitely not 2. It's definitely not 3 either. It's between 2 and 3. All right. So let's talk more about implicit. I want to do that one. That's kind of funky. No, I don't. Let's look at this next one. Sure. So the thing about implicit differentiation is it's really a lot of algebra. Like the first step is kind of find the derivative of both sides. The rest of it's do the algebra. And yeah, so in this next example, we'll talk about both. Sure. So let's look at, let's do this one. Let's find the derivative of the following equation. X squared plus xy plus y squared equal to 12. And we'll also find the second derivative just because it's worth talking about. So I want to find the derivative. And again, when we write this, we are assuming that y is a function of x. Right? So we're always making the assumption that x is the independent variable and y is the dependent variable. So when I differentiate this, I'm just going to use my usual rules. Derivative of x squared is 2x. X times y, I'm going to have to use the product rule. Derivative of x is 1. Y is y. Plus x, right? So I take the derivative of x, leave y alone, leave x alone, and the derivative of y is the derivative of y. Plus the derivative of y squared is 2 times my stuff to the first times the derivative of my stuff equal to 0. And then we solve for y prime. So I like to underline or circle or something the y primes and leave those on the same side. So I'm going to have x times y prime plus 2y times y prime equal to negative 2x minus y. And then I'm going to factor out the y prime. So we got y prime times x plus 2y equals negative 2x minus y. And finally, solving for y prime, negative 2x minus y over x plus 2y. So that would be my first derivative. And then you could use this to find the slope of the tangent line at any point you wanted that we knew was on the curve. So for example, no, I guess not really. Not for example. Okay. So I guess you could say, what's the slope at the point, say which is a point. No, it's actually not. Never mind. Trying to make a point that's actually on there, but it's not actually on there. So I'll just leave it. Well, let's talk about the second derivative, because the second derivative of implicitly is always kind of funky. So I want to find the second derivative. And 99 times out of 100, you're going to have to use the quotient rule. Because 99 times out of 100, your first derivative is a quotient because you had to do this process where you're dividing by a thing. So let's write this on the other side so we have enough room. Oh, and then and then times, there's some funkiness that happens sometimes. So, let's use orange. I've used orange in a while. So we have y prime, which is negative 2x minus y over x plus 2y. And now I'm going to take the derivative of that. So y double prime is the derivative of all this. Negative 2x minus y over x plus 2y. And so I'm going to use the quotient rule. So it's going to be the bottom times the derivative of the top, which I'm just going to write as negative 2x minus y prime, minus the top times the derivative of the bottom, which is x plus 2y prime, all over the bottom squared. Okay, so now let's fill in the blank, or let's do a little more. So this is going to be x plus 2y times, all right, what's the derivative of negative 2x? It's negative 2. What's the derivative of negative y? It's negative y prime. It's negative y prime. So it's minus all of this garbage. So the problem with this, the hard part about the second derivative is whenever you take the derivative of y again, the derivative of y is y prime, but we know what y prime is, so we have to substitute that in. Right? That's my y prime right there. Minus negative 2x minus y times the derivative of x plus 2y, which is 1 plus 2 y prime. All over x plus 2y. So that's your second. So, and then typically there's probably some simplification we can do, but it's just so gross. I know there's, let me look real quick in the textbook, because I know there's one example specifically that's always kind of like, how did they get that in the answers? And I want to kind of talk about that one because I think it's worthwhile. I don't see the one I'm thinking of. That's too bad. Yeah, that's unfortunate. So I would leave it at that personally. So the only thing you can do, which is probably the one thing I would do, is you can multiply everything by x plus 2y. But then it's just like, it just gets real messy. But that's how you do a second derivative implicitly. Gosh, time just wants to fly right on by. Sure. So let's look at another example. I want to find, oh yeah. Sorry, one sec. Sure. So find slope of the line tangent to, what do we got here? Where'd you go? Sure, I guess that's fine. X squared y plus y cubed equal to sine of Wow, brain work. Sorry. Sine of x plus x squared at point 0, 0. Okay. There's a reason I'm asking this question, and because I want to show you something that kind of is easy. So we're going to start off the way we always do. Well, I should say, right? Slope of the tangent line, also known as the derivative, at this point. So we're going to take the derivative. So I'm going to get 2x times y plus x squared times the derivative of y, which is y prime. I'm using the product rule here. Plus 3y squared times y prime equal to derivative sine of x is cosine of x plus derivative of x squared is 2x. Now we're going to solve for y prime. So let's see, I've got this piece here, I've got this piece here, those are my y primes. So I'm going to bring this to the other side, and I might as well factor out the y prime from these pieces. So I get y prime times x squared plus 3y squared equal to cosine of x plus 2x minus 2xy. And then if we solve for y prime equals cosine of x plus 2x minus 2xy over x squared plus 3y squared. And now we're a little bit worried because I wanted to find the slope of the tangent line at that point there. If I plug in 0, 0, what do I get? See, cosine of 0 is 1 plus 2 times 0 minus 2 times 0. I get 1 on top. And on the bottom, I get 0 plus 0, which is 0. What does it mean? My slope is 1 over 0. My slope is undefined. So a better question to have asked wouldn't have been find the slope, but find the equation of the tangent line. Because if you have an undefined slope, what kind of tangent line do you have to have? Vertical. So if I have an undefined slope, I have a vertical tangent line, which means the tangent line is, well, if it's a vertical line, it's x equal to something. It's got to go through that point, so it has to be x equal to 0. So sometimes weird things happen. This isn't exactly the weird thing I meant to happen, but it is what happened here. What I wanted to say, which I'll say in the next example, is sometimes, not here, instead of having to solve for y prime, you can actually just plug in your point right away. The issue that we would have run into here if we had plugged in 0, 0 is we would have gotten 0 plus 0 plus 0 equals 1 plus 0. And so if you get 0 equal to 1, it actually means you're in this situation where you have a vertical tangent line. On the other hand, let's do another example. One that is not so terrible. Yeah, we got enough time, right? Yeah, we got enough time. So let's say I want to find the, actually, let's go equation of the line tangent to the following. Sure, let's go x cubed y plus 3y minus x to the fourth equal to, let's see, x squared y squared plus 27, 9, sure, 18. At the point 3, comma 1. Sorry, yeah, that's right, yeah, 3, comma 1. Okay. So here's what I want to point out, because this is kind of useful sometimes. If they're asking you to find the equation of a tangent line at one point, they're only asking you to find the slope at that one point. They don't actually care about us finding the derivative everywhere. It's kind of like the difference between finding the derivative of the point versus finding the derivative of the function. When it's a regular derivative, sure, it's easy just to find the derivative and plug in the point. When it's implicit like this, it's often easier to start finding the derivative and then immediately plug in the point. Here's what I mean. So let's differentiate. So we differentiate both sides. A lot of these have the product rule in them. So the derivative of x cubed y, product rule. Derivative of x cubed is 3x squared times y plus, now we flip it, x cubed times what's the derivative of y? It's the derivative of y. Okay, here it's a little more complicated. I have to use the chain rule. Derivative of 3x minus y to the fourth is going to be 4 times my stuff to the third power. Sorry, my stuff is 3y minus x times the derivative of that stuff. The derivative of 3y is 3y prime. Derivative of x is 1. Equal to x squared, y squared. I have to use the product rule. Derivative of x squared is 2x times y squared plus x squared times the derivative of y squared, which is 2y times y prime, which doesn't fit. Sorry. It's 2y times y prime plus 0, right? Because the derivative of 18 is 0. Be careful. A lot of times people accidentally leave that. They forget that, oh yeah, I'm differentiating that 18. That 18 has a derivative that's 0. And now, here's what I want to do. I do not want to solve for y prime. There's a lot of algebras, right? There's a y prime there. There's a y prime there. I probably have to distribute this like that. That seems awful. And then there's a y prime over here. I really, really don't want to solve for y prime. And I really, really don't have to. So what I can do is I can actually now plug in x equal to 3 and y equal to 1. Right? Because I'm trying to find the derivative when x is 3 and y is 1. It doesn't matter if I plug in x equal to 3 and y equal to 1 now or after I've done the algebra. So if x is 3, I'm going to get 3 times 9 times 1 plus x is 3, that's going to be 27 times y prime plus, check this out, if x is 3 and y is 1, 3 minus 3 is 0. And this whole term is a big 0. Equal to x is 3, y is 1. So I get 2 times 3 is 6, times 1 squared is 6. Plus x squared is 9, times 2 times y is times 2 times 1 times y prime. Right, so I'm not plugging in for the y primes because I don't know what y prime is, right? I'm solving for y prime. But now look at this. This is so much easier to solve for y prime. So if you're asked to find the slope of the tangent line or the equation of the tangent line at a particular point and not asked to find the derivative in general, it's a really good idea to do the one step of differentiating and then immediately plug in the point where you're trying to find the tangent line at. Because typically it's going to make the rest of the algebra or arithmetic super, super easy. So then we get, let's see, 27 plus 27y prime equals 6 plus 18y prime. And subtracting 18y prime gives me 9y prime. 6 minus 27 is negative 21. So y prime equals negative 21 over 9, which is negative 7/3. And then we can find the equation of the tangent line by saying, okay, well, here's the point, and the slope is negative 7/3. So the equation of the line is going to be, using the point slope form, y minus 1 equals negative 7/3 times x minus 3.